Hey guys, I'm going to go through the Chapter 10 review. Should be pretty easy, not going to lie, but alright, so for the first one, a normal distribution has a mean of 28 and a standard deviation of 3. Find the probability that a randomly selected x value from the distribution is in the given interval. And so for this one right here, you can use the empirical rule. So the empirical rule we learned all the way back in 10.1a, and this was the empirical rule. So if you have data, it's normally distributed, meaning that it is symmetrical. If you have the mean and the standard deviation, you can find probabilities that a randomly selected data value, if you have like exactly 1, 2, or 3 standard deviation values, then you can estimate probability of selecting a data value. So you can use that, or you can use the Desmos function, which is what I'm going to do. It's what I encourage you guys to do and what you guys will be allowed to use on the exam, and that's to use Desmos. So in Desmos, whenever you're here, you can see in the bottom right where we have the enter, the delete, and the arrow buttons. Just above the arrow buttons, you have the functions. So if I click on that functions right here, and we move down to distributions, and in the top left of the distributions, there's normal dist for normal distribution. And so we're going to click on here, and just below normal distribution, you can see mean equals 0, standard deviation equals 1. That's just talking about this curve right here. We can click into the parentheses and we can edit what we want the mean and the standard deviation to be. So in our set, we have 28, and then we're going to do comma, and we're going to do 3 for the standard deviation. And then to the left of, just below the red marker, the red graph, in this line right here, there's a magnifying glass with a plus button. If you click on that, it will zoom in. It will zoom into your curve. And you can kind of see that we have just at the center, there's 28. That's our mean. And every 3 units along the x-axis is the standard deviation. And then we're going to click the drop-down arrow where it says cumulative probability. And we can now calculate area underneath the curve, which is equivalent to probability. And the first question says, what's the probability that we can select an x value that is between 19 and 34. And so you can see these regions right here. Whenever it says between, we're going to be using inner, meaning in between 2 values. And so the 2 values we want are 19, and here we're going to do 34. And then you can see that to the right of our inequality, it says 0.976. And so we would put that as our answer. And if you want, you can put it as a percentage, or you can leave it as a probability. I don't really mind, but I'll say here 97.6%. And then less than 31. So going back to Desmos right here, if it's less than, then for the region we want to calculate, it's going to be to the left, and we're going to put in 31. So the probability of that is 84.1%. And then more than 34, so going back here, if it's more, we're going to select the right region, and then we're going to do 34, and we get 2.3%. Okay, and pretty much that easy. The times at a restaurant takes to prepare its quick lunch specials are normally distributed with a mean of 3 minutes and a standard deviation of 0.5 minute. About what percent of customers have their quick lunch between 2 minutes and 4 minutes? So if I go back here, let's edit the data from our table. We have a mean of 4, and we have a standard deviation of 0.5. I'm going to zoom in as well so you can see that the curve has been adjusted accordingly, and so we want in between. So we're going to do inner, and we're going to do between 2 and 4. So you can see 2 is all the way over here. There's not a whole lot, but 2 to 4. I feel like the mean is not 4, the mean is 3. There we go. So that makes a lot more sense. All right, between 2 and 4, we have 95.4%. So about 95.4% of these customers will get their quick lunch between 2 to 4 minutes. About what percent of customers have their quick lunch in less than 2 minutes? So we'll go here. We're going to do less than 2. It's already there. So less than 2 minutes, 2.3%. All right. So in this part right here, use the z-score table or Desmos. So I don't know. I guess I could provide z-score tables for anyone that wants it, but I would just recommend that you guys use Desmos. I'm not going to go over how to use the z-score, just because I have allowed you guys to use Desmos. That's the way I taught. That's the way I recommended here. So z-scores, the z-score table, that orange sheet, if you still remember, great. I guess I can just suggest that the formula is z is equal to the mean. No, it's equal to x minus the mean over the standard deviation. So you can calculate z-scores and then put it into your table to find the probability. And so the reason why you might need to use the z-score is because in this case right here where we have 175, you just need to find how many standard deviations this is away from the given mean and then calculate the probability from the table. But we're just going to use Desmos. It's so much easier. We don't need to calculate z-scores, and just nice. So with Desmos, the two functions that you want to use is either, I'm going to edit this, and we actually don't need this function at all right here. We just need the normal distribution, which is what we've been using. So individual scores in a bowling league are normally distributed with a mean of 191.8 and a standard deviation of 13.8. So let me go into Desmos and edit my function here. So it's 191.8, and then it was 13.8 as the standard deviation. All right, and then I'm going to go ahead and zoom to the appropriate part. All right, find the probability that a player will bowl under 175. So just come in here and do 175 and to the left. And so the probability is about 11.2%. So we'll say 11.2%. Find the probability that a player will bowl over 220%. So we'll go in here. We'll do 220, make sure that we do it to the right, and the probability is 2.1%. Find the probability that a player bowls between 190 and 200. So we'll do inner, we'll do 190 and 200, and that's 27.6%. You can see just how quickly Desmos can calculate these probabilities. Really nice. What score would a bowler have to get to be in the 90th percentile? So for this one right here, it's giving me that there is a 90% chance. So 90%. And so think about your normal distribution. It's asking what score. The scores are on the x-axis. And so like in Desmos, whenever I'm here, so the percentage of 27.6 right here, there's the scores between 190, so if I go here, the scores between 190 and 200 are 27.6%. Now we have to work backwards. They're telling us that what score would a bowler have to be in the 90th percentile. So what that means is that the area underneath the curve to the left has to be 90%. So this has to be 90%. and then what would the score have to be. So Desmos can also calculate this for us, but on the left side where we see the inner, outer, left, and right, that says region. To the right it says compute area. If we switch this over to say compute bounds, now it's doing the opposite. So notice how on the bottom below that you have the calculations where you input the scores, so 190 and 200, and it gives you the probability. If you switch it to bounds, it makes it so that you can type in the the percentage, I should say 0.9. There we go, that's why it was giving me a hard time. So we can't do 90%, we have to do 0.9. Okay, now we have to be careful here. So this is 0.9, and it's the inner 0.9%, meaning that to the right would be 5%, and to the left would be 5%. For the, let's not worry about outer, but to the right, you can see to the right is 90%, to the left would be 10%. But we want it so that the left is 90%. So what score would a bowler have to be to get to the 90th percentile? And so in this case right here, we're going to say left. And so you can see how that lines up. We have 90% on the left, and what would be the score? So according to here, you can kind of see how close it is, but on to the left side where we typed in 0.9, it says the x value has to be less than 209.5. And so we'll just round that up and say 210. So you'd have to score 210 to be in the 90 percentile. So this is just where you have to work backwards. But yeah, if there are 60 members, how many of them are likely to score above 220? Round to the nearest person. So there are 60 members. So keep this in mind right here, that we can't end up with a number more than 60. So there are only 60, and how many of them are likely to score above 220? So notice here that we already calculated the probability up in number 7, so that we don't have to do another probability. But the probability is 21.2%, which is 0.021 probability, and I'm going to multiply that by the number of people. So basically what I'm trying to find is 2.1% of 60. So what is 2.1% of 60? So 0.021 times by 60, and I get 1.26. And so I'll probably just round down. So one person in this group of 60 are likely to get above a 220. Okay. All right, and that's all you need Desmos for. Moving on, identify the population and the sample. So the population is the whole, sample is a subset. So in a university, a survey of 1641 students found that 479 of them do not know the name of their college mascots. So we're talking about the university, so I would say that the population is the university. And I would say for the sample is how many are being surveyed. That's the 1641. Now, in the sample, 479 of them do not know the name of their mascot, but the actual sample is how many were surveyed. So this is not the sample right here. In the United States, a survey of 1,000 households with at least one child found that 1,874 of them have at least 2 computers. So we're talking about the United States, so I would just say for the population, that's, yeah. So for the population, I would just say the U.S. And then I guess you could say U.S. households maybe. But yeah, for the sample, that would be the 1,000 households that were surveyed. And of the 1,000, 1,874 of them have at least 2 computers. Determine whether the numerical value is a parameter or a statistic. So a parameter is a number that is describing the population, and a statistic is a given number that is describing the sample. And so in these problems right here, you're going to pay attention to the number, and does the number have something to do with the population or the sample? So on a high school football team, 2% of the players are vegetarian. This 2% is referring to the entire high school football team, meaning that the high school football team is the population, and this 2% is of the population. So therefore, the 2% is a parameter. So it's a numerical descriptor of the population. And then the average amount of the surveyed utility bills, notice here it says surveyed utility bills, so we don't have all the utility bills, which means that this right here has to be a statistic. It's a numerical descriptor of the sample. So a numerical descriptor of a sample is a statistic. A numerical descriptor of the population is a parameter. Identify the type of sample as random, self-select, systematic, stratified, cluster, or convenient. So there are 6 of these right here. A bank wants to know whether its drive-through customers are satisfied with the service. Customers receive a code on their receipt that allows them to go online and fill out a survey. This would be a self-select because people that go online, they don't have to respond. It's voluntary response, and so that's a self-select. People volunteer who want to participate. A school wants to know whether high school teachers prefer before school or after school faculty meetings. 10 teachers with classrooms near the front office are surveyed. So the tricky thing about this one here, it says near, which means that they are only collecting information from those that are close by. And so they're basically just doing this out of convenience. Who's the closest to get to? And so, yeah, convenience, I would say. For 17, identify the sample and explain why the sample is biased. So it is a biased sample. We have to explain why. So every 5th customer that walks into a locally owned hardware store answers a survey that asks for opinions about lowering taxes for locally owned businesses to increase the likelihood that they can stay open for business. So this is a systematic. A systematic is whenever there's a rule, so every 5th customer, that's a rule that is followed that determines who's selected. So systematic, and why is it biased? Because they are they're asking their own customers. Who likely want them to stay in business. So you'd probably want to ask people outside of the business, generally just the general public, not just people that shop at your store. A fitness center wants to find out whether members would sign up for an afternoon yoga class. It surveys the first 20 members on the alphabetized member list. And so I would say that this is convenience. And why is it biased? Well, so these members are alphabetized, so they're only getting ones at the top of the list, which people that share the same last name might be, family members, relatives, and therefore they might try and they might have similar times, and so they might have pretty much the data could be biased based on what those people want. So skipping we're just skipping a big portion, I guess. Skipping or excluding, I guess I should say excluding a portion of the class, excluding a portion of the class. I'll just say that, and then I don't really want to type out what I just said, but there we go. 19. Every fourth passenger. Determine whether the sample is biased and explain why or why not. And so, every fourth passenger who boards an airplane is asked whether they like the new method of seat assignment. So, it's systematic. I don't think we have to say that. Describe the sample. Determine whether the sample is biased. So, I would say no. The sample is representative. And a lot of students will say, well, what if you have a bad seat? What if you have a good seat? Well, that's kind of the idea, is that you want input from everybody. And so if every fourth passenger, you don't know what kind of seat that they have, it's unknown, and they're being asked whether they like the new method. So some people might say yes, some people might say no. But that's kind of the idea. It's going to be representative of the whole population. Some are going to say yes, some are going to say no. We're not just going to ask people who got the good seats or who's the people who just got the worst seats. We're trying to get people who got both, and so that we can get a fair, a non-biased sample. So I would say it's not biased. Your teacher is choosing 4 students to participate in a pizza eating contest. The names of all 30 students are put in a hat, and 4 names are randomly drawn from the hat. So I would say also not biased. Samples random. And there's no sort of favoritism or anything like that going on. So I would say that's not biased either. A researcher is considering 3 methods of evaluating 2 different types of fertilizer for corn. Classify each method as a survey, an experiment, or an observational study. Then identify which method would be most reliable and explain your reasoning. So, 1. Randomly divide rows of corn in the same test field into 2 groups. Put fertilizer in one group of rows and record the yield for those rows and for the rows without the fertilizer. Draw conclusions based on your finding. So that sounds pretty experimental. You are creating 2 different groups, one with a control and one that's control and one that has a treatment. For 2, choose some of the rows of the corn at random from a field. Determine which type of fertilizer has been applied in the past and what the yield is for each row. Extrapolate the findings to the whole field. And so this would be a survey, because we're only looking at some of the rows at random. So in an observation and in a experiment, it's likely that you're going to use everything. Experiment, obviously there's some sort of treatment. Observational study, you're just merely observing effects. But a survey will just take some of it and then apply the finding to the whole thing. And so, yeah, that's a survey, which means 3 is likely an observational study. So monitor the yield of all rows of corn in various test fields, so all of them, being fertilized with the product chosen by the farmer. Record the yield for those rows. And so in this case, yeah, that's an observation. But notice here, so as far as which one would we pick to be most reliable, so I would say an experiment. It's something that we can so the good thing about experiment is that the bad thing I should say about an observation is that you can't necessarily say that there's a cause and effect relationship. So that's what, if an experiment is done well, then you eliminate variables, then there's a stronger cause and effect. And so we want the strongest possible cause and effect answer that we can get. So I would say the experiment for cause and effect. Your explanation might be different, and I am totally open to a good explanation. So, determine whether the study is a randomized comparative experiment. If it is, describe the treatment group, and the control group. If it is not, explain why not, and discuss whether the conclusions drawn from the study are valid. To test the effect of using a computer for testing, 300 students are randomly divided into two groups. One group is tested using paper and pencil, and one group is tested using the computer. After analyzing the test results, it was found that the average test scores in both groups were not significantly different. And so, yes or no, is this a randomized comparative experiment? I'm going to say yes. It is randomized, and so that's a good thing. We have a control, we have a treatment. So the treatment here is the computers. And the treatment groups are the computer group. So I'm just going to repeat and just say computers. And the control group is the pencil and paper. Okay. At a health fair, people can choose to enroll in 6 months in a 6-month eating plan. 60 people who choose to eat 6 vegetables a day plan were monitored for 6 months, as were 60 people who choose the drink 12 glasses of water a day. At the end of the 6 months, people who chose the drink 12 glasses of water a day had 20% lower cholesterol than the people in the other group. And so I would say this is not random, obviously, because there are those that are chosen. People chose their groups. And are the conclusions valid? No, the conclusions are not valid. There could be other variables. And that's all I would say. There could be other variables as to why this group had 20% lower cholesterol. Maybe the people that drink 12 glasses of water a day are generally more healthy. They have different habits than the one with 12. They might not, but the thing is, we don't know because it wasn't random and those people chose. Explain whether the research topic is best investigated through an experiment or an observational study. A cycling team wants to know whether incorporating yoga into the workout routine improves racing times. Let's see, probably experiment. I don't see any reason why that wouldn't be the best. A researcher wants to compare the effects of new experimental cancer drug with a cancer drug that has been used for at least 10 years. So this sounds like, it honestly sounds like experiment initially, but whenever you think about that they're testing it, comparing it with the cancer drug that has been used for at least 10 years, then that would be an observation. You're collecting data that's already there and you're looking at the data, so observational. You're also not creating the groups yourself randomly and having a placebo or something like that, having a control group and an experimental group. So it definitely does sound experimental, but that would be observational. A researcher wants to test whether stretching after exercising decreases the number of injuries due to muscle damage. The researcher selects 400 people who exercise on a regular basis. The people are divided into two groups based on age. Within each age group, the people are randomly assigned to stretch after exercising or to not stretch. The people's occurrence of injuries due to muscle damage is monitored. The stretching after exercise significantly decreases the number of injuries due to muscle damage. So identify a potential problem with the experiment. So they divided the people by age, so based on age for stretching, and people generally that are older have a harder time stretching. So I would say older people might have a harder time stretching. And could injure easily. I'll say get hurt. Easily. Describe how you could improve the design. Don't divide by age. Maybe you can just make a random assignment. Maybe. If you have anything else that you'd like to add, make sure you do so. All right. In a survey of 1022 U.S. adults, 76% said that more emphasis should be placed on producing domestic energy from solar power. What is the margin of error? So in this case right here, we're talking about 76% of a population here. So this is population proportion. We're talking about a certain percentage of a survey, and we're trying to represent that with the population. So population proportion. And so in that case right here, there's a formula for the margin of error for a population proportion, and that is plus or minus 1 over the square root of n, and n is the population sample size. So what is the margin of error? It's going to be plus or minus the square root of 1022, 1 over square root of 1022. And so 1 divided by the square root of 1022. And I have, that's equal to 0.0313, I guess we could say. Now, and then in the next question it says, give an interval that is likely to contain the exact population proportion. So the exact population proportion is likely to be between, so this was the population proportion of the sample of this 1022. And so we're saying that of this sample, 76%, but what about the population? So what we're going to do is we're going to take our estimate and we're going to add and subtract from it our margin of error. And that's what we think, that's where we think the exact population proportion is. It's somewhere between here. But I'm also going to change this to percentage because that's what it's supposed to be. And so this would be 3.13%. So I'm going to add that to here. So we're going to do 76 plus 3.13. And I get 79.13%. And then I'm going to do 76 minus 3.13. And I get 72.87%. And so the exact population proportion we think is somewhere between these values right here. Before the Thanksgiving holiday, 2368 people were surveyed and asked what they were thankful for, and 85% said their family. What is the margin of error for the survey? And so what we're going to do, we're going to do plus or minus 1 over square root of 2368. So 1 divided by the square root of 2368. And I've got that's equal to 0.021, and so, or about 2.1%. And so give an interval that is likely to contain the exact population proportion of people who would say this. So we think that we would take the 85% and we're going to add on the 2.1, so it's going to be 87.1%, and then we'll take the 85 and we'll subtract the 2.1 and we'll get 82.9%. So that's where we think the exact population proportion is, somewhere between those two percentages. All right, in a study, 20 randomly selected managers were found to spend a mean time of 2.4 hours per day on paperwork. The standard deviation of the 20 was 1.3 hours. Construct a 99% confidence interval for the mean time spent on paperwork for all managers. And so in this case, we're talking about the mean margin of error. And the mean margin of error is different, where the margin of error is equal to plus or minus, and we're going to take z times by the standard deviation divided by the square root of n. And z has to do with our level of confidence. So there's 3 z values that we would use for 99%. I think it's like 2 point... let me check it. They will be given to you on the test, so keep that in mind. But they were from the 2.6. So 99%, 2.576. So 2.576 is the z value that we will use. So we'll do 2.576 times by 1.3 all over the square root of 20, which was our sample size. So our margin of error, so 2.576 multiplied by 1.3 and divided by the square root of 20, and I get 0.749. Do not convert this to a percentage because we're not applying the mean. We're not applying the margin of error to a percentage. We're applying it to the actual value of the mean. And so what we're going to say is that for the confidence interval, the interval of the exact mean is going to be somewhere between. So we're going to take our margin of error and add it and subtract it from 2.4. So we'll do 2.4 plus our margin of error, and I get 3.1, I'll just say 3.15. And then we'll do 2.4 and we will subtract our margin of error, and I get 1.65. So we're saying that the mean time of our sample of the 20 was 2.4, but we think the mean time of the population would be between 1.65 and 3.15. A random sample of 19 women, so we have our sample size. 19 women results in a mean height of 63.85. So we're saying the mean height, so this is x bar. Other studies have shown women's height are normally distributed with a standard deviation of 2.5. So there's our standard deviation. And we're trying to construct a 90% confidence interval. And so we're going to use a z value of 1.645. So z is equal to 1.645. Okay, so we'll say that for our margin of error is going to be 1.645 times by 2.5 divided by the square root of 19. So 1.645 times by 2.5 divided by the square root of 19, and I get 0.943, I guess. So here is our margin of error. Our sample mean is given there. We think the exact mean, so we're going to do the 63.85 and we'll add our margin of error, and we get 64.79, and we'll take the samples, so 63.85, and we will subtract our margin of error, and we get 62.91. So we think the exact mean is somewhere between those two values. Okay, and that should be everything for the review. Good luck.